Since the earliest days of science, humanity has sought to understand not only how the universe arose, but also why it exists exactly in the form we know. Among the countless questions that challenge physicists, astronomers, and cosmologists, one stands out for its depth: the asymmetry between matter and antimatter. The fundamental laws of physics, confirmed by experiments and by equations that describe the creation and transformation of particles, indicate that the universe should have emerged in perfect balance between the two sides of this cosmic coin. For every particle of matter, an antiparticle should have been created, with the same mass properties but opposite charges. When they meet, these entities annihilate in a flash of energy, leaving only radiation. By that logic, the universe should not contain galaxies, stars, planets, or life. The final result should be only a homogeneous ocean of energy, silent and without structure. Yet when we observe the cosmos at every scale, from the immensity of galaxies to the atoms that form our bodies, we find a universe dominated by matter. This means that at some point in cosmic history, a tiny imbalance occurred, but one sufficient to define everything we know. This difference is not merely an academic curiosity, it is the reason we exist. Life, mountains, seas, and even human consciousness are direct consequences of this enigma. Without it, there would be no narrators, listeners, or viewers, only emptiness. In this video, we will explore in depth this problem that has intrigued generations of scientists. We will trace the conceptual foundations of matter and antimatter, examine the theoretical conditions required for a slight advantage of matter to arise, analyze the leading models that seek to explain the asymmetry, and discuss modern experiments that try to reveal the answers hidden at the heart of the universe. At each step, we will maintain a calm and detailed pace, building a solid and scientific narrative, ideal for learning, reflecting, and relaxing at the same time. The goal is to show that behind the apparent simplicity of existence lies a cosmic paradox. The universe should not be here, and yet it is. Before diving into the possible explanations for this enigma, it is necessary to clearly understand what matter and antimatter are. Matter is what makes up everything around us: the fundamental particles that form atoms, the atoms that form molecules, the molecules that form life and inanimate objects. Among the elementary particles of matter, we find electrons, which orbit around nuclei composed of protons and neutrons. Protons and neutrons, in turn, are made up of quarks, smaller particles that interact through the strong nuclear force. All these entities share properties such as mass, electric charge, and spin, which are fundamental quantities in physics. Antimatter is the exact counterpart of this system. For every particle of matter, there exists an antiparticle with identical mass but opposite charge. The electron with negative charge has as its pair the positron with positive charge. The proton with positive charge has as its counterpart the antiproton with negative charge. The neutron, which has no net electric charge, also has an anti-neutral version composed of antiquarks. When a particle and its antiparticle meet, the result is annihilation. Both disappear, converting all of their mass into energy in the form of high-intensity radiation. This process is one of the most efficient conversions known in nature, transforming 100% of mass into energy. As described by the famous equation of equivalence between mass and energy, this balance between matter and antimatter is not just a mathematical prediction. It was confirmed in laboratories since the beginning of the 20th century, when the positron was detected in cosmic rays and later reproduced in particle accelerators. Today, we are able to produce antiprotons and even antiatoms, such as antihydrogen, under controlled conditions. This demonstrates that antimatter is real and follows the same fundamental laws as matter. The question is not whether it exists, but why it is not found in abundance across the cosmos. This conceptual clarity is crucial because it allows us to realize that the absence of large-scale antimatter does not arise from the impossibility of its existence, but from a profound imbalance that occurred at the origin of the universe. When analyzing the creation of the universe in the very first instance after the initial event, we find a scenario in which intense energy was constantly converting into pairs of particles and antiparticles. High-energy physics states that under conditions of extreme temperature and density, such as those present at the beginning, the production of matter and antimatter should have been perfectly balanced. There was no apparent reason to favor one side over the other. This symmetry reflects the principle of conservation of fundamental properties such as electric charge. If a positive particle appeared without a corresponding negative one, the global balance would be broken, violating conservation laws that support the entire framework of physics. For this reason, scientists expected the universe to contain equal amounts of matter and antimatter. But if that had truly been the case, the cosmos would have evolved in a very different way. Each particle of matter would have encountered a corresponding antiparticle, and together they would have annihilated, transforming into pure radiation. The final result would be a universe without galaxies, without stars, without planets, and without life. Only a uniform sea of photons, cold and impersonal. However, this is not the reality we observe. The universe is full of luminous galaxies, rich in gas and dust, where stars are born and die, giving rise to heavy chemical elements that accumulate in planets and form the foundation of life. This means that at some point in the primordial process, a small difference emerged. For every billion pairs of particles and antiparticles created and annihilated, only one particle of matter remained. This leftover was enough to build the entire visible cosmos. This microscopic asymmetry, seemingly irrelevant, is responsible for the grandeur of today's universe. The great scientific question is, what caused this tilt of the balance? The theories known so far do not satisfactorily explain how this small advantage of matter over antimatter appeared. That is why the problem is so profound. It is not merely a curiosity, but a challenge to the foundations of physics and to our understanding of reality. If theory suggests that matter and antimatter should have arisen in equal amounts, then observation of the universe should confirm this symmetry. However, when we point our telescopes toward the depths of the cosmos, what we see is a disconcerting reality. All galaxies, stars, and gas clouds observed to this day are composed of matter. There are no clear signs of extensive regions formed of antimatter. If they did exist, collisions between particles and antiparticles would inevitably occur at their boundaries, resulting in annihilations that would release enormous amounts of radiation at very specific frequencies. That radiation should be detectable by our modern instruments, which are already capable of recording faint signals from events billions of light years away. Yet this signature simply does not appear. This cosmic silence is disturbing because it reinforces the idea that antimatter almost completely vanished. Observations made by satellites that analyze cosmic background radiation, by telescopes that study gamma rays, and by cosmic ray detectors spread across Earth show no evidence of gigantic domains of antimatter coexisting with matter. If galaxies made of antimatter existed, collisions with clouds of interstellar matter would produce energetic flashes that would be perceptible, leaving unmistakable marks in the sky. The fact that we do not see these signals implies that the universe is dominated by matter at practically every accessible scale. The great question troubling cosmology is precisely this: why is the visible universe asymmetric when it should be balanced? This is not a matter of detail or measurement error. The evidence is consistent and repeated across different observations and different eras of science. This paradox forces researchers to find an explanation that goes beyond what is predicted by the current set of theories. The problem is that none of the known symmetries is sufficiently violated to justify such a difference. What is observed is a cosmos that contradicts the most basic expectations of fundamental laws. This contradiction is one of the greatest driving forces behind contemporary research in particle physics and cosmology. For to understand why the balance tilted in favor of matter is to understand why we ourselves exist. To understand why the problem of asymmetry between matter and antimatter challenges modern physics, we must carefully examine what is called the standard model of particle physics. This model is the most complete theoretical framework ever built to describe the behavior of fundamental particles and the forces that act between them. It did not emerge in a single moment, but was consolidated over decades of experiments and discoveries, especially between the years 1960 and 1980, when different theories about forces and interactions were unified into a coherent framework. The Standard Model classifies all known particles into two major groups, fermions and bosons. Fermions are the matter particles, such as quarks and leptons. Quarks form protons and neutrons, which in turn make up atomic nuclei. Leptons include the electron, fundamental to the structure of atoms, and neutrinos, which pass through matter almost without interacting. Bosons, on the other hand, are the mediator particles of the fundamental forces. The photon is responsible for the electromagnetic force. The W and Z bosons carry the weak force. The gluons keep quarks bound inside protons and neutrons through the strong nuclear force. And the Higgs boson gives mass to particles by interacting with the so-called Higgs field. Despite its complexity, this framework describes with extraordinary precision the phenomena we can observe in laboratories and particle accelerators. Tests carried out in experiments such as those at the Large Hadron Collider confirm predictions of the Standard Model with minimal margins of error. This solidity makes the model one of humanity's most impressive intellectual achievements. However, there is a crucial point. Although the Standard Model explains almost everything we observe, it fails in one fundamental aspect, precisely the one that interests us in this video. It does not offer a satisfactory explanation for the difference between matter and antimatter in the universe. This happens because the symmetries embedded in the Standard Model are, in essence, almost perfect. The model allows for small symmetry violations, such as the so-called charge parity violation, observed in certain decays of unstable particles. But these violations are so subtle that they do not come close to justifying the cosmic imbalance required for matter to have survived over antimatter. In other words, the Standard Model predicts a universe far more balanced than the real universe. This discrepancy forces scientists to search for explanations beyond the accepted model, exploring new particles, new fields, and even new forces that might be hidden, but which may have played a decisive role in the initial moments of creation. Thus, the Standard Model is at once one of the greatest victories and one of the greatest limitations of modern physics. It allows us to calculate with great accuracy the behavior of the particles that make up ordinary matter, but it also reminds us that we still do not understand why matter exists in excess compared to antimatter. This gap is one of the reasons why so many current experiments, spread across different parts of the world, are searching for signs of phenomena that escape the reach of the Standard Model. Discovering such signs would not merely add a new piece to the puzzle, but might even reformulate the very framework that sustains our view of the origin of the universe. In 1967, the Russian physicist Andrei Sakharov presented a proposal that would become one of the most influential ideas in the attempt to solve the enigma of asymmetry between matter and antimatter. He formulated three fundamental conditions that would need to be satisfied in the primordial universe for an imbalance in favor of matter to arise. These conditions, known as the Sakharov conditions, are today a theoretical guide that shapes practically all modern hypotheses about the origin of the cosmic difference. Without the simultaneous fulfillment of these three requirements, any theory that seeks to explain the predominance of matter would be incomplete. The first condition is the violation of baryon number. The baryon number is a property that counts the amount of particles called baryons, which are protons and neutrons, in comparison to their antiparticles. In a perfectly symmetric universe, this number should be conserved. However, for there to be more matter than antimatter, it would be necessary to break this conservation at some point, allowing physical processes to favor the creation of more matter particles than antimatter particles. Without this violation, the balance would always remain equal, and the result would be a universe empty of structures. The second condition is the violation of charge and parity symmetries, as well as the combined symmetry of charge, parity, and time. In physics, charge symmetry means that the laws should be the same if particles were exchanged for antiparticles. Parity symmetry means that the laws should be the same if spatial orientation were inverted. Time symmetry indicates that equations should remain the same if time flowed backwards. To generate a universe dominated by matter, it was necessary for nature to violate these symmetries in certain specific processes. This breaking would allow particles and antiparticles not to behave in exactly the same way, creating the possibility of a subtle but decisive imbalance. The third condition of Sakharov is that the universe must have gone through states outside thermodynamic equilibrium. This means that at some moment, cosmic conditions were not stable and uniform, but dynamic, with rapid transformations of energy into matter. These moments of disequilibrium are fundamental because they allow physical laws to act differently from what would be expected in a perfectly balanced system. The primordial universe, with its extreme temperatures and rapid phase transitions, provided exactly this type of environment, creating the stage where small symmetry breakings could transform into a macroscopic difference between matter and antimatter. These three conditions are not just an exercise in logic. They are the foundation that guides modern experiments and theories. Every new physical model, whether related to undiscovered particles, exotic fields, or subtler interactions than those already known, must respect this tripod proposed by Sakharov. That is why, to this day, physicists dedicate their careers to testing processes that could violate the baryon number, to seeking new examples of symmetry violation, and to recreating, in accelerators, out-of-equilibrium environments that may imitate the conditions of the early universe. Sakharov's brilliance was to transform a cosmic enigma into a concrete physics problem, with three clear criteria that continue to guide the search for answers. To understand how the universe managed to favor matter over antimatter, it is essential to grasp two fundamental concepts of modern physics: charge parity violation and the combined violation of charge, parity, and time. These symmetries, which initially seemed absolute, represented the expectation that nature should treat particles and antiparticles in the same way, and that physical laws should remain unchanged even under inversions in space and time. However, experimental discoveries throughout the 20th century showed that this view was naive. Nature, in very specific situations, does not respect these symmetries, and precisely in these small breaches may lie the key to explaining why we live in a universe dominated by matter. Charge symmetry states that if we swapped all particles for their antiparticles, the behavior of interactions should remain the same. Parity symmetry states that the laws of physics should remain unchanged if space were reflected as in a mirror. For a long time, both were believed to be inviolable, until experiments carried out in the 1950s demonstrated unequivocally that parity symmetry is not respected in weak interactions, which are responsible for processes such as the radioactive decay of certain nuclei. Later, it was verified that charge symmetry was also not preserved in all circumstances. The most surprising discovery came when scientists observed that combined charge and parity violation occurred in particles known as strange mesons. This result was a shock to physics and opened the way to understanding that nature has mechanisms that differentiate particles from antiparticles. But even this violation is not enough. Thus arises the need to also analyze time symmetry. According to this symmetry, the fundamental equations should remain valid if the flow of time were inverted. However, more refined experiments showed that charge parity violation automatically implies the violation of charge, parity, and time symmetry. This means that the very arrow of time, on a microscopic scale, is related to subtle differences in the behavior of particles and antiparticles. This realization has profound implications. Without charge parity time violation, the universe could never have developed the imbalance necessary for matter to survive. The problem is that although these violations exist and have been measured in experiments with unstable particles, such as beauty mesons and strange mesons, their intensity is extremely small. Analyses show that the degree of violation detected so far is not capable of explaining the enormous difference observed between the amount of matter and antimatter in the cosmos. This means there is something beyond what we already know, perhaps new particles, new fields, or new interactions not yet revealed. This search drives high-energy physics experiments around the world, because identifying an additional source of charge parity time violation would be a crucial step toward unraveling the enigma of our very existence. Among the four fundamental forces that govern the universe, the strong nuclear force occupies a central role. It is responsible for keeping quarks bound inside protons and neutrons, and at the same time, for holding protons and neutrons together within atomic nuclei. This force is described by what is called quantum chromodynamics, a highly precise theory that explains how gluons, the mediator particles of the strong force, interact with quarks. Quantum chromodynamics predicts the possibility of a significant violation of charge and parity symmetry. In simple terms, if this violation were as intense as some calculations suggest, the universe should present clear signs of imbalance within the strong sector. Such a violation could even decisively contribute to explaining the predominance of matter over antimatter. However, when scientists analyze the behavior of atomic nuclei and measure physical quantities associated with charge parity violation, they find a surprising result. This violation is extremely small, much smaller than expected. This enigma is known as the problem of charge parity violation in the strong sector. If quantum chromodynamics allows the existence of this violation, why does nature seem to almost eliminate it? This contradiction has intrigued physicists for decades and led to the formulation of hypotheses that seek to explain why the strong sector is so symmetric when it should not be. One of the most influential proposals to solve this issue is the existence of a theoretical particle called the axion boson. This hypothetical boson would serve the function of restoring symmetry in the strong sector, automatically adjusting the equations of quantum chromodynamics to eliminate the violation that should be present. The idea that axions exist does not only solve the problem of charge parity violation in the strong sector, but it also connects to another major question in cosmology: the nature of dark matter. Axions could make up part or even all of this invisible substance that dominates the mass of the universe, uniting two cosmic mysteries into a single hypothesis. The problem of charge parity violation in the strong sector is a clear example of how apparent gaps in theories can point toward new horizons. The absence of measurable violation suggests that hidden mechanisms are acting at scales we still do not understand. Solving this issue would not only help us understand the balance between matter and antimatter, but could also reveal a new class of particles and fields that would radically expand our knowledge of physics. That is why laboratories around the world search for indirect signs of axions and conduct sensitive experiments to detect this particle. The science so far is challenging, but each experimental limit narrows the path and brings us closer to the truth about one of the greatest enigmas of the universe. Among the most decisive instants in cosmic history is the moment when the universe went through what physicists call electroweak symmetry breaking. In the very first moments after creation, when temperatures were unimaginably high, the fundamental forces did not appear as we know them today. The electromagnetic force and the weak force, for example, were unified in a single interaction. As the universe expanded and cooled, a phase transition occurred, and this symmetry broke, separating the electromagnetic force from the weak force. This event, which shaped the physics of elementary particles, also created special conditions that could have favored the production of more matter than antimatter. It is in this context that the concept of electroweak baryogenesis arises. Baryogenesis is the theoretical process that explains the origin of baryonic asymmetry, that is, the predominance of protons and neutrons in relation to their antiparticles. During the electroweak transition, the universe did not remain in perfect equilibrium. This departure from equilibrium is one of Sakharov's conditions for creating the difference between matter and antimatter. Furthermore, theory predicts that certain interactions between particles and fields could have violated the baryon number and also the charge and parity symmetries, providing fertile ground for cosmic asymmetry. In practical terms, it means that the very structure of known physics in its most primitive phases could contain the necessary ingredients to resolve the paradox. However, the most precise calculations carried out within the framework of the Standard Model show that the intensity of violations obtained in this scenario is not sufficient to explain the magnitude of asymmetry observed today in the universe. This means that electroweak baryogenesis, although an attractive hypothesis, does not close the account on its own. For it to actually produce the excess of matter, some additional mechanism would be necessary, such as new particles, new fields, or interactions beyond those predicted by the Standard Model. This limitation opens space for bolder proposals, which try to expand the theory and introduce elements capable of reinforcing the process of generating asymmetry. Even with these difficulties, electroweak baryogenesis remains one of the most studied scenarios. This is because it connects directly to phenomena that we can investigate in laboratories, such as the dynamics of the Higgs field and the behavior of massive particles in high-energy colliders. Experiments at the Large Hadron Collider and other accelerators seek clues of processes that could indicate a stronger symmetry breaking or new forms of interaction capable of amplifying the asymmetry. Discovering such signals would be revolutionary, as it would allow us to link the initial instance of the cosmos to results measured directly in our laboratories. Electroweak baryogenesis, therefore, is not just a hypothesis about the distant past. It is a living line of investigation, one that can transform our understanding of the universe and reveal why it exists dominated by matter. Among the most promising hypotheses to explain the predominance of matter over antimatter is leptogenesis, a scenario that places neutrinos as the protagonists of cosmic history. Neutrinos are extremely light and enigmatic particles, almost invisible, that cross ordinary matter with virtually no interaction. Millions of them pass through your body every second without leaving any perceptible trace. Yet, despite this apparent indifference, neutrinos may have played a fundamental role in the fate of the universe. Leptogenesis is based on the idea that, in the early cosmos, asymmetry did not arise directly between protons and antiprotons, but rather between leptons and antileptons, particularly neutrinos and their antimatter counterparts. This initial asymmetry would then have been converted into an excess of baryons, that is, into an excess of ordinary matter. To understand how this would work, it is necessary to return to the instant when the universe was an incandescent ocean of particles and fields. At that time, there may have existed much heavier versions of neutrinos, now called heavy or high-mass neutrinos. These unstable neutrinos would have decayed asymmetrically, slightly favoring the production of leptons over antileptons. This difference, although minimal, already created an imbalance in the lepton sector. The next step is the conversion of this leptonic asymmetry into baryonic asymmetry through quantum processes known as sphalerons, which violate baryon number and can transform part of the difference into an excess of protons and neutrons. Thus, leptogenesis offers an indirect but plausible route to explain why matter won the battle against antimatter. The beauty of this hypothesis lies in the fact that it connects phenomena of the primordial universe to current properties of neutrinos. We know, for example, that neutrinos have mass, even if extremely small. This discovery, made at the end of the 20th century through the study of neutrino oscillations, was a shock to physics, because the standard model predicted neutrinos without mass. This unexpected detail opens the possibility that neutrinos are Majorana particles, meaning that each neutrino is its own antiparticle. If this is true, the link with leptogenesis becomes even stronger, as it reinforces the idea that neutrinos carry within them the ability to generate fundamental asymmetries in the cosmos. From an experimental point of view, testing leptogenesis is a huge challenge. We cannot directly recreate heavy high-mass neutrinos in laboratories, since they would have existed only under the extreme conditions of the primordial universe, but we can search for indirect clues. Experiments dedicated to observing the so-called neutrinoless double beta decay attempt to verify whether neutrinos are truly Majorana particles. If this process is confirmed, it would be powerful evidence that leptogenesis has solid foundations. In addition, increasingly precise measurements of neutrino masses and oscillations may provide crucial indications of how these particles contributed to the fate of the universe. Leptogenesis is a remarkable example of how particle physics and cosmology intertwine. By studying almost imperceptible particles which cross the Earth without resistance, we may find answers to the greatest of questions: why we exist. If neutrinos truly hold the secret of the asymmetry between matter and antimatter, it would mean that the universe, in its earliest state, chose to favor matter thanks to the behavior of particles so subtle that we can barely detect them today. It is a powerful reminder that the greatest cosmic structures may depend on the most delicate details of nature. Neutrinos are among the most mysterious particles ever discovered by science. Unlike electrons, protons, and neutrons, which make up all visible matter, neutrinos interact almost not at all with the rest of the universe. They are produced in abundance in nuclear processes, such as the reactions that occur in the interior of stars or during stellar explosions known as supernovae. They also appear in controlled nuclear reactions in reactors and in collisions of cosmic rays with Earth's atmosphere. Despite this constant production, their interaction with matter is so weak that trillions of neutrinos pass through our bodies every second without us being able to feel them. This characteristic makes neutrinos incredibly difficult to detect and study, but also suggests that they may conceal fundamental secrets about the structure of the cosmos. For a long time, it was believed that neutrinos had no mass. This assumption was embedded in the standard model of particle physics, which explained the known behavior of these entities up to that point. However, at the end of the 20th century, experiments carried out in Japan and Canada showed that neutrinos change identity as they travel, oscillating between three different types: the electron neutrino, the muon neutrino, and the tau neutrino. This phenomenon can only occur if neutrinos have mass, even if very small. This discovery revolutionized physics because it showed that the standard model was incomplete and opened a new window of possibilities for understanding the origin of the asymmetry between matter and antimatter. One of the most intriguing hypotheses is that neutrinos are Majorana particles. This means that each neutrino would be both particle and antiparticle at the same time. Unlike electrons and positrons, which are distinct entities, a Majorana neutrino would be its own counterpart. This characteristic would have profound implications for cosmic balance, as it would allow processes that violate the conservation of lepton number, one of the conditions identified by Andrei Sakharov as necessary to create the asymmetry between matter and antimatter. If neutrinos really are Majorana particles, the path to leptogenesis, and therefore to explaining the predominance of matter, would become even more plausible. But how can this hypothesis be tested? One of the most important strategies is the search for the so-called neutrinoless double beta decay. In this process, two neutrons in an atomic nucleus would transform into two protons, emitting two electrons without releasing neutrinos. This type of decay would only be possible if neutrinos were Majorana particles. To this day, no experiment has conclusively detected this phenomenon, but searches continue with increasingly sensitive instruments buried deep underground or shielded with lead to minimize interference from other radiation. A confirmation of this decay would be one of the most important discoveries in the history of physics, because it would directly connect the microscopic properties of neutrinos to the macroscopic fate of the universe. Studying neutrinos is also about investigating a link between the infinitely small and the infinitely large. These almost invisible particles may have influenced the structure of the cosmos since the very first instance after its creation. They remind us that the fate of stars, galaxies, and even life itself may depend on the behavior of entities so subtle that they pass through matter without leaving a trace. The Majorana question remains open, but each step taken in its investigation brings us closer to an answer to the greatest of questions: why matter exists instead of only dispersed energy. To understand how the asymmetry between matter and antimatter may have arisen, it is essential to reconstruct the chronology of the primordial universe, step by step, from the instance closest to the moment of creation to the formation of the first chemical elements. This timeline allows us to identify when the conditions predicted by Andrei Sakharov, violation of baryon number, violation of charge, parity, and time symmetries, and states out of equilibrium, could have manifested. At the same time, it shows how small breaks at critical moments could have been amplified to the point of defining the cosmic destiny. In the first trillionths of a second, the universe was an incandescent sea of pure energy, so dense and so hot that particles such as protons and electrons did not yet exist in stable form. In this scenario, energy was constantly converting into pairs of particles and antiparticles in a process of continuous creation and annihilation. Shortly after, in an equally tiny fraction of time, the so-called cosmic inflation occurred, a dizzying expansion that multiplied the size of the universe in an almost unimaginable way. This process, in addition to smoothing irregularities, also created out-of-equilibrium conditions that would later prove crucial for the formation of asymmetry. When the universe reached the mark of 1/100th of a second, the temperature had dropped enough for protons and neutrons, made of quarks, to begin to stabilize. At this point, processes of baryon number violation could have acted, favoring a slight difference in favor of matter. Between 1 second and a few minutes, primordial nucleosynthesis began, forging the first nuclei of hydrogen, helium, and traces of lithium. The chemistry of the cosmos was beginning to take shape, but the balance of matter was already defined, a small excess that survived the near-total annihilation. Without this excess, there would have been no nuclei to form, and the universe would be nothing more than a sea of radiation. About 380,000 years later, The universe had cooled enough for electrons to bind to nuclei, forming the first neutral atoms. This era, known as recombination, allowed radiation to decouple from matter, leaving behind what we now observe as the cosmic microwave background, a photograph of the young universe. This radiation carries within it the marks of the asymmetry established in the first instance, functioning as a window into the distant past. By analyzing it, scientists confirm that the excess of matter over antimatter was already consolidated long before the formation of the first stars and galaxies. This chronology shows that the question of asymmetry is not a secondary detail, but a determining factor from the very first pulses of the universe. Each stage, inflation, the formation of protons and neutrons, nucleosynthesis and recombination, carries within it clues about when and how the balance tilted in favor of matter. The challenge is to identify at what moment Sakharov's conditions were fulfilled, and whether this occurred through mechanisms already predicted, such as electroweak symmetry breaking, or if it depends on phenomena beyond the standard model. By reconstructing the chronology of the primordial universe, we not only understand our origin, but also reveal the fragility and improbability of existence itself. Among the most extraordinary episodes in the history of the primordial universe is the so-called cosmological inflation. This term refers to a process of accelerated and almost unimaginable expansion that occurred in an extremely short fraction of time, long before the formation of the first atoms and even before primordial nucleosynthesis. It is estimated that inflation took place between approximately 10 to the minus 36 seconds and 10 to the minus 32 seconds after the birth of the cosmos. In this tiny interval, the universe increased in size by an incalculable factor, growing from subatomic dimensions to something much larger than entire galaxies. This dizzying expansion explains why the universe is so uniform on large scales, and at the same time, why small density fluctuations were able to give rise to stars and galaxies. From the point of view of the matter and antimatter problem, inflation is particularly important because it creates out-of-equilibrium conditions, one of Andrei Sakharov's 3 requirements. During inflation, the universe expanded so quickly that any particles present were diluted into immense scales. Soon after, at the end of this process, what scientists call reheating occurred. At this stage, the energy of the inflationary field was converted into particles and radiation, replenishing the universe with matter and antimatter in massive quantities. It is at this moment that new mechanisms of symmetry breaking could have acted, favoring a slight predominance of matter. Reheating, therefore, is not just a detail of cosmic history, but a decisive point in the search for answers. Another fascinating aspect of inflation is that it not only expanded the universe, but also amplified small quantum fluctuations, transforming them into seeds for the cosmic structure we see today. Galaxies, clusters, and even the voids between them were born from these microscopic variations. This means that the very process that explains the architecture of the cosmos may also be linked to the asymmetry between matter and antimatter. If certain quantum fields involved in inflation interacted asymmetrically with particles and antiparticles, the result could have been a minute but crucial difference in favor of matter. Even today, cosmological inflation is a theory in development. It explains many of the observed aspects of the universe, such as its homogeneity and isotropy, but raises new questions. One of them is whether different inflationary mechanisms could produce distinct amounts of matter and antimatter. Another question is whether reheating generated exotic particles, such as heavy neutrinos or hypothetical bosons, which may have served as triggers for leptogenesis or other scenarios of asymmetry creation. In summary, inflation and reheating are inseparable phases of cosmic chronology. They provide the stage on which the conditions necessary for the imbalance between matter and antimatter could have occurred. Without inflation, the universe would have been too chaotic to sustain structures. Without reheating, there would not have been enough particles to build stars and planets. By analyzing these two processes together, scientists not only investigate the origin of asymmetry, but also try to understand how the universe transformed from a microscopic quantum state into an immense and ordered cosmic reality. Primordial nucleosynthesis is one of the most revealing phases in the history of the cosmos. and also one of the stages that provides us with direct evidence of the imbalance between matter and antimatter. This process occurred between approximately 3 minutes and 20 minutes after the birth of the universe, when temperatures dropped enough to allow protons and neutrons to combine and form the first stable atomic nuclei. It was during this short interval of time that the initial abundances of light elements were established: hydrogen, helium, deuterium, and traces of lithium. These proportions did not arise by chance. They are the direct result of the physics governing the primordial universe and of the amount of matter that remained after the near-total annihilation with antimatter. If the symmetry between matter and antimatter had been perfect, there would not have been enough protons and neutrons for the formation of nuclei. The universe would have become a space filled only with radiation. But calculations show that for every billion pairs of particles and antiparticles created in the first instance, only one particle of matter remained unmatched. This tiny surplus was enough to compose all the stock of protons and neutrons that participated in nucleosynthesis. The result was the creation of a universe with approximately 75% hydrogen and 25% helium, in addition to minimal amounts of deuterium and lithium. These values match remarkably well with observations made today in ancient stars and primordial gas clouds, confirming that the excess of matter was established before this phase. The study of primordial nucleosynthesis is one of the most powerful tools of modern cosmology because it offers a natural laboratory for testing hypotheses about cosmic asymmetry. If more antimatter had survived, the abundance calculations would not coincide with observations. The agreement between theory and empirical data shows that the balance of matter in relation to radiation was defined even before the formation of the first nuclei. This means that the conditions identified by Andrei Sakharov, the violation of baryon number, the violation of charge, parity, and time symmetries, and the departure from equilibrium, had already acted at some point between the initial instant and the first minutes of the universe. Furthermore, nucleosynthesis provides clues about processes beyond the standard model. Small discrepancies in the abundance of lithium, for example, raise the hypothesis that exotic particles may have influenced the process, modifying the balance between protons and neutrons. This detail, known as the primordial lithium problem, still puzzles scientists and may be a sign of new physics. At the same time, deuterium, extremely sensitive to baryonic density, serves as a precise ruler to measure the total amount of ordinary matter in the cosmos. The fact that its values agree with observations of the cosmic microwave background reinforces the consistency of the framework. Thus, primordial nucleosynthesis is not only a historical stage, but also direct proof that we live in a universe where matter won the battle against antimatter. The atoms that make up our bodies and the oxygen we breathe are direct descendants of this small surplus of protons and neutrons. Studying the chemistry of the young universe is, therefore, a way of understanding the roots of our very existence. Every hydrogen nucleus in your body is a silent witness that, at some point, perfect balance was broken. And it is precisely in this microscopic detail that the explanation for the macroscopic greatness of the cosmos is found. The cosmic microwave background is one of the most solid pillars of modern cosmology, and one of the most direct proofs that the asymmetry between matter and antimatter was already established long before the formation of the first stars. It is an extremely faint but uniform radiation that permeates the entire universe and reaches us from all directions in the sky. It was emitted about 380,000 years after the birth of the cosmos, when the universe had cooled enough to allow electrons to bind to protons and helium nuclei, forming the first stable atoms. This process, known as recombination, released the photons that until then had been trapped in constant interactions with matter. Since then, these photons have traveled freely through space, carrying with them a clear picture of the conditions of the young universe. The importance of this radiation for the matter and antimatter problem lies in its small variations in temperature and density. By analyzing these variations, we can measure the amount of ordinary matter present in the universe at that time, as well as determine the ratio between matter and radiation. Observations made by satellites such as the Wilkinson Microwave Anisotropy Probe and Planck show that the universe contains about 5% ordinary matter, also called baryonic matter. This value coincides with the calculations made from primordial nucleosynthesis, reinforcing the conclusion that the excess of matter was defined in the first instance and remained constant until hundreds of thousands of years later. Another essential aspect is that the cosmic microwave background does not show signs of large regions composed of antimatter. If entire galaxies were made of antiparticles, the boundaries between matter and antimatter would produce intense emissions of gamma rays, which would alter the observed pattern of this background radiation. The fact that we do not find such distortions is further evidence that the cosmos is dominated by matter, confirming that antimatter practically disappeared on large scales. The background radiation, therefore, is a silent witness to the victory of matter in the primordial universe. Beyond providing answers, the cosmic microwave background also raises new questions. Its minute temperature variations reveal the role of cosmic inflation and quantum fluctuations that became seeds for galaxies. These same fluctuations could have carried subtle traces of processes that created the asymmetry. Some scientists search these variations for signs of symmetry violations not yet identified, which could indicate the presence of new particles or fields beyond the standard model. Although there is still no conclusive evidence, the increasing precision of instruments may in the future reveal details that remain hidden. In summary, the cosmic microwave background functions as a cosmic archive, a faithful record of when the universe stopped being opaque and became transparent. By studying it, we have direct access to the conditions of a time when asymmetry was already consolidated. It confirms that matter prevailed over antimatter, and at the same time, reminds us that this triumph does not yet find complete explanation in current theories. This is why the background radiation is considered not only a portrait of the past, but also an invitation to decipher the enigmas that still persist in the present. One of the most natural hypotheses, when confronted with the absence of antimatter in our cosmic neighborhood, would be to imagine that it did not disappear completely, but that it is concentrated in distant regions of the universe. According to this idea, there could be entire galaxies made of antiprotons, antineutrons, and positrons, forming stars and even planets composed exclusively of antimatter. If this were true, the universe would have been divided into large domains, some of matter and others of antimatter. At first, this scenario could solve the apparent contradiction between theory and observation. However, there is a fundamental problem. If such domains really existed, their borders would be zones of intense destruction. At the interface between a galaxy of matter and a galaxy of antimatter, particles and antiparticles would constantly meet and annihilate, producing enormous amounts of high-energy radiation. This process should generate flashes of gamma rays so intense that they would be easily detected by our telescopes. However, we do not observe anything that matches this prediction. The visible universe, measured in all directions, shows no signs of the presence of such borders. This means that if domains of antimatter exist, they must be separated by distances so immense that they are, in practice, inaccessible to any direct observation. Another way to test this hypothesis is to analyze the cosmic microwave background, which works as a photograph of the universe when it was only a few 100,000 years old. This radiation is extremely uniform, and if there were significant regions of antimatter, annihilations at the borders would have left clear marks on the observed pattern. Once again, the silence of the data reinforces the conclusion that antimatter is not hidden in large quantities in remote parts of the observable universe. Experiments searching for signs of antinuclei in cosmic rays also help to clarify the issue. So far, positrons and antiprotons have been detected on a small scale, which can be explained by common astrophysical processes such as particle collisions in stellar explosions. However, a complex nucleus of antimatter, such as antihelium, has never been found in significant amounts. The absence of this type of signal is further evidence that there are no galaxies or stars made of antimatter nearby. Therefore, the idea of domains of antimatter remains only as a possibility in extremely speculative scenarios in which universes separated by vast distances beyond our observable horizon could contain significant concentrations of antimatter. Within the universe we can explore with our telescopes, the evidence converges on a single conclusion. We live in a cosmos dominated by matter. This realization reinforces the enigma even more because it eliminates the simple hypothesis that antimatter is just hiding somewhere far away. The problem is not one of location, but of origin. The question remains, why did the universe choose matter and not perfect symmetry? Although we do not find galaxies or stars made of antimatter, we know that small amounts of it are naturally produced in high-energy astrophysical processes. These manifestations do not solve the problem of cosmic asymmetry, but they offer important clues and act as natural laboratories to study the properties of antimatter. The most evident place to search for such signals is in cosmic rays, extremely energetic particles that travel through space and constantly hit Earth. Detectors installed on balloons, satellites, and space stations reveal that mixed with protons and atomic nuclei of matter, positrons and antiprotons also appear, clear evidence that antimatter continues to be produced in small amounts in different corners of the universe. The origin of these positrons and antiprotons can largely be explained by particle collisions in extreme astrophysical environments. When high-energy cosmic rays collide with atoms of interstellar gas, the collision energy is sufficient to create pairs of particles and antiparticles. In this process, positrons and antiprotons appear as natural byproducts. Supernovae, pulsars, and active black holes can also generate environments where particles are accelerated to speeds close to the speed of light, favoring the small-scale production of antimatter. These mechanisms explain most of the signals already detected, but leave open the possibility that part of the observed antimatter may have a more exotic origin. One of the most discussed hypotheses is that certain excesses of positrons in cosmic rays could be linked to the annihilation or decay of dark matter particles. If this were confirmed, it would represent a direct connection between the mystery of dark matter and that of antimatter. Experiments such as the alpha magnetic spectrometer, installed on the International Space Station, have already recorded distributions of positrons that are not fully explained by conventional astrophysical processes alone. Although these results are not yet conclusive, they encourage the search for signals of new physics beyond the standard model. Another crucial point is that, despite the detection of antiprotons and positrons, no significant amount of heavy antinuclei, such as antihelium, has ever been observed in cosmic rays. Detecting even a single antihelium nucleus in abundance compatible with ordinary astrophysical origin would be virtually impossible, and its discovery would indicate the existence of macroscopic reservoirs of antimatter somewhere in the universe. So far, none of these nuclei have been found, reinforcing the conclusion that cosmic antimatter is restricted to tiny quantities produced in high-energy collisions. The presence of antimatter in cosmic rays, therefore, confirms that the process of particle-antiparticle pair creation still happens naturally in the current universe, but the scale is so small that it does not solve the central paradox of cosmology. These detected particles are sparks in the midst of an ocean of matter. The universe as a whole remains dominated by ordinary atoms, and the antimatter we find is only an ephemeral trace of local energetic processes. Even so, studying these traces is essential, because every detected antiproton or positron is an opportunity to learn about the most extreme environments of the cosmos, and possibly to glimpse new physical laws that bring us closer to answering the enigma of the origin of asymmetry. If antimatter hardly exists in large quantities in the observable universe, science has found a way to produce it artificially. The creation of antimatter in the laboratory is an extraordinary achievement of modern physics, as it requires recreating conditions similar to those of the primordial universe, even if on a microscopic scale. The process occurs mainly in particle accelerators, gigantic machines that collide protons or electrons at speeds close to the speed of light. In these extremely high-energy collisions, part of the kinetic energy is converted into matter and antimatter, obeying the principle that energy can be transformed into particles. Thus, in each event, pairs appear formed by a matter particle and its corresponding antiparticle, such as electrons and positrons or protons and antiprotons. The first experimental signs of antimatter in the laboratory appeared as early as the beginning of the 20th century, when the positron was detected in cloud chambers and soon reproduced in controlled collisions. Decades later, in 1955, physicists succeeded in producing and identifying antiprotons, consolidating the idea that every particle truly had a counterpart. From that point on, controlled production became routine in large accelerators. Today, The largest research center in this field is CERN in Switzerland, where colliders such as the Large Hadron Collider and the Antiproton Decelerator not only create antiparticles, but also decelerate and trap them for detailed studies. One of the greatest recent advances was the creation of entire antiatoms such as antihydrogen. To achieve this, scientists produce antiprotons and positrons separately, and then make them combine under carefully controlled conditions. The result is an antiatom that can be studied and directly compared with its matter equivalent. This comparison is vital for testing fundamental symmetries. If a hydrogen atom and an antihydrogen atom present even minimal differences in their properties, it would indicate a profound violation of the symmetries we know and could help explain the origin of cosmic asymmetry. Despite these achievements, the production of antimatter is extremely limited. Each antiproton created consumes an immense amount of electrical energy, much greater than the energy that could be released in its annihilation. This makes it impossible to think of antimatter as a practical energy source, contrary to what often appears in works of science fiction. It is estimated that, in all experiments ever carried out, the total amount of antimatter produced is smaller than a grain of sand. This tiny scale makes it clear that the function of producing antimatter in the laboratory is not to generate fuel, but to answer fundamental questions about the laws of the universe. Each antiparticle generated and trapped represents a unique opportunity to explore symmetries, test theories, and search for differences between matter and antimatter. This is how physicists hope to find clues as to why the cosmic balance tilted in favor of matter. Creating antimatter in the laboratory is not only an impressive technological feat, but also a window into the past of the universe, when particles and antiparticles appeared in abundance at every instant. By repeating on a microscopic scale what happened on a cosmic scale, scientists hope to decipher the enigma of our very existence. Producing antimatter is already a gigantic challenge, but storing and manipulating it is even more complex. Unlike ordinary matter, antimatter cannot come into contact with any surface made of usual particles. The simple encounter between an antiproton and a proton, or between a positron and an electron, leads to immediate annihilation, releasing energy in the form of radiation. Thus, any physical container made of matter would automatically be destroyed the instant it touched antimatter. Solving this dilemma required the creation of highly sophisticated techniques involving the use of magnetic and electric fields to keep antiparticles suspended in a vacuum without touching the container walls. One of the most effective solutions is the so-called penning and Paul traps. These devices use combinations of magnetic and electric fields that create stable regions in space capable of trapping charged particles such as positrons and antiprotons. Inside these traps, antiparticles are confined in circular or oscillating trajectories, prevented from escaping or colliding with the container's matter. Under ideal conditions, it is possible to keep antiprotons trapped for minutes or even hours, long enough to perform high-precision measurements. These experiments require temperatures close to absolute zero, since the colder the particles are, the easier they are to control and the less tendency they have to escape. The next step is the formation of antiatoms such as antihydrogen. In this case, antiprotons and positrons are combined and maintained in special magnetic traps known as neutral magnetic traps, since antihydrogen, being electrically neutral, cannot be confined by electric fields alone. The Alpha collaboration at CERN succeeded in 2010 in trapping antihydrogen atoms for long seconds, opening the way for increasingly sophisticated experiments. Since then, much longer confinement times have been achieved, allowing detailed studies of the spectral and gravitational properties of antimatter. Despite these advances, storing antimatter in macroscopic quantities remains impossible. To this day, it has never been possible to accumulate more than a tiny number of antiparticles at the same time. Any attempt to store antimatter on a larger scale would face almost insurmountable challenges, both technical and energetic. This means that current experiments are conducted with microscopic quantities, enough only to test fundamental laws of physics. Even so, these tests are crucial, since comparing the properties of matter atoms with those of antihydrogen can reveal subtle symmetry violations, offering clues about the origin of cosmic asymmetry. Manipulating antimatter also involves additional challenges. For example, by releasing trapped antiatoms under controlled conditions, it is possible to observe how they respond to Earth's gravitational field. This type of experiment helps verify whether antimatter falls in the same way as matter, an essential test to confirm the universality of gravity. Furthermore, experiments aim to measure the spectral frequencies of antihydrogen with extremely high precision to check whether they coincide exactly with those of ordinary hydrogen. So far, no differences have been found, but scientists continue to refine their techniques, as any deviation, even minimal, could pave the way for new theories beyond the standard model. In summary, the storage and manipulation of antimatter are carried out under conditions of extreme control, involving near-perfect vacuums, temperatures close to absolute zero, and highly sophisticated magnetic traps. These efforts do not have the practical goal of accumulating fuel or creating energy sources, but rather of understanding the foundations of reality. Every trapped antiproton and every studied antiatom is an opportunity to investigate why the universe favored matter. Manipulating antimatter in the laboratory is therefore more than a technological challenge. It is a window into the deepest history of the cosmos and into the mystery of our very existence. One of the greatest motivations for producing and storing antimatter in the laboratory is the possibility of making direct comparisons between atoms of matter and atoms of antimatter. These studies are crucial because they test, with the highest possible precision, one of the most fundamental principles of physics, the symmetry between particles and antiparticles. If hydrogen and antihydrogen atoms showed any measurable difference in their basic properties, it would mean that nature subtly favors matter over antimatter. Such a discovery would be groundbreaking, as it would provide a natural explanation for the cosmic imbalance observed since the very first instance of the universe. Experiments carried out in major research centers, such as CERN, are dedicated precisely to this objective. After trapping antiatoms in magnetic traps, scientists can measure their spectral properties, that is, the frequencies of light they absorb or emit. In the case of ordinary hydrogen, these spectral lines are known with extremely high precision, the result of decades of studies. By comparing the spectrum of antihydrogen with that of hydrogen, physicists can verify whether the symmetry between matter and antimatter is truly perfect. So far, all results indicate no difference within the limits of precision achieved, but the margins continue to shrink with each new experiment, keeping open the possibility of a future discovery. Beyond the spectrum, another line of investigation involves measuring the gravitational behavior of antihydrogen. The question seems simple: does antihydrogen fall toward Earth in the same way as hydrogen? But the answer has profound implications. If antimatter were to respond differently to gravity, it would require a radical revision of the most basic physical theories, including general relativity. Experiments such as Alpha G are dedicated to releasing antihydrogen atoms under controlled conditions to observe their motion under the action of the gravitational field. Initial results confirm that antimatter falls the same way as matter, but scientists continue to refine precision to eliminate any margin of doubt. These measurements are complemented by studies of magnetic properties. The magnetic moment of particles such as the antiproton can be compared with that of their matter equivalents. Any difference, even minimal, would reveal a symmetry violation that could be linked to the conditions that favored matter in the primordial universe. Once again, no discrepancies have been found so far. This does not mean that the problem is solved, but that the violations required to explain the asymmetry must be extremely subtle or perhaps depend on phenomena not yet accessible to current instruments. The importance of these measurements is that they transform the question of asymmetry into something testable, verifiable, and repeatable. Instead of remaining only in the realm of cosmological hypotheses, the problem can be addressed in laboratories on Earth, where particles and antiparticles are recreated and directly compared. Each technological advance, each improvement in the ability to trap antimatter for longer or to measure its properties with greater precision, represents a step towards solving one of the deepest enigmas of physics. Thus, the study of antiatoms is not just an exotic curiosity, but a solid scientific path to investigate the roots of our existence. If one day a concrete difference is found, even in the most extreme decimal places, it could shed light on why matter survived over antimatter in the universe. And if no difference is ever detected, it will mean that the answer to the enigma lies in even deeper phenomena, beyond the current frontiers of physics. In either case, experiments with antiatoms remain one of the most promising keys to unraveling the mystery of cosmic asymmetry. Among all the questions surrounding antimatter, one of the most intriguing is whether it responds to gravity in the same way as ordinary matter. Traditional physics, based on Albert Einstein's general relativity, states that gravity must be universal. This means that any object with mass, whether made of protons, electrons, and neutrons, or of their corresponding antiparticles, should fall toward a source of gravity in the same way. This principle, known as equivalence, is one of the pillars of modern science. However, since we have never had access to large amounts of antimatter, this prediction remained without direct experimental confirmation for decades. The possibility that antimatter could react differently to gravity is small, but it cannot be dismissed without tests. In recent years, experiments conducted in major laboratories such as CERN have been dedicated to answering this question definitively. By trapping antihydrogen atoms in magnetic traps, scientists developed methods to release these atoms under controlled conditions and observe their motion under the influence of Earth's gravitational field. The Alpha collaboration, for example, managed to carry out direct measurements showing that antihydrogen falls downward, confirming that antimatter feels gravity in the same way as ordinary matter. These initial results already represent a historic achievement, as they provide the first experimental evidence that gravitational equivalence also applies to antimatter. Despite this advance, scientists are seeking increasingly precise measurements. The question is not only whether antimatter falls, but whether it falls with exactly the same acceleration as matter. Any difference, even the smallest one, would have enormous implications. It could indicate the existence of new forces or subtle interactions not accounted for in the standard model. It could also open doors to theories that connect the enigma of cosmic asymmetry with still unknown properties of gravity. This possibility keeps the scientific community mobilized, investing in technologies capable of trapping antiatoms for longer periods and measuring gravity's effect on them in more detail. Beyond theoretical interest, this question also captures popular imagination. Speculation often arises that antimatter could fall upward or escape Earth's gravitational field, behaving in the opposite way to matter. Although experiments have already ruled out this extreme hypothesis, there is still room to investigate subtle differences. The future of this research will depend on the ability to build instruments sensitive enough to detect deviations as small as 1 part in 100,000, or even 1 part in 1 million in the gravitational acceleration applied to antimatter. In summary, current experiments show that gravity acts on antimatter in the same way it acts on matter, confirming the traditional view. However, the search for minimal deviations continues, because even an infinitesimal difference could radically change our understanding of the universe. Testing antimatter's gravity is more than confirming a known law. It is exploring the boundary between the established and the unknown in search of clues that might explain why we exist in a cosmos dominated by matter. To investigate the origin of the asymmetry between matter and antimatter, scientists turn to unstable particles known as mesons. These particles are composed of a quark and an antiquark, and they exist in several families, including strange mesons and beauty mesons. The interest in these particles arises because their decays reveal violations of charge and parity symmetries, as well as the combined symmetry of charge, parity, and time. Since these violations are directly linked to Andrei Sakharov's necessary conditions, studying mesons becomes a practical way to observe in the laboratory processes that may have occurred in the primordial universe. The story begins in 1964, when charge and parity violation was observed for the first time in the decays of strange mesons, also known as kaons. This discovery shocked physics, because until then, it was believed that fundamental laws treated particles and antiparticles identically. Decades later, more advanced experiments showed that charge and parity violation also occurs in beauty mesons, known as B mesons. These measurements confirmed that nature truly makes subtle distinctions between matter and antimatter. This microscopic difference, even if small, could be one of the keys to understanding how matter became dominant. Today, particle accelerators, such as the Large Hadron Collider in Europe, and B factories in Japan and the United States produce immense quantities of beauty mesons and strange mesons to study their decays with extremely high precision. The idea is to observe how these unstable particles transform into others and compare the decay rates between particles and antiparticles. Any discrepancy detected represents a violation of symmetry. The results obtained so far show that these violations do exist, but the measured intensity is still far too small to explain the gigantic cosmic imbalance that favored matter. Despite this limitation, meson experiments are of inestimable value. They confirm, under controlled conditions, that nature is not perfectly symmetrical. They also provide concrete clues on how to improve theoretical models. If new forms of charge, parity, and time violation are discovered in these decays, this could indicate the presence of particles or interactions that are not yet known. This is why international collaborations continue to expand their detectors, increase the statistics of recorded events, and refine mathematical analyses. Each meson that disintegrates in fractions of a second inside a detector is like a window into the universe's past. By examining these unstable particles, we are trying to reproduce in the laboratory the conditions that existed in the very first cosmic instance. Although the definitive answer has not yet emerged, research with beauty mesons and strange mesons remains one of the most promising approaches to deciphering why the universe contains galaxies, stars, and life, instead of being just a homogeneous sea of radiation. Among the most subtle and at the same time most powerful methods to investigate the asymmetry between matter and antimatter is the search for electric dipole moments in fundamental particles. In simple terms, an electric dipole moment is a measure of how the electric charge of a particle would be distributed internally. For symmetric objects such as electrons, protons, or neutrons, this distribution is expected to be perfectly uniform, so that there is no preferred axis separating positive and negative charges. However, if an electric dipole moment were detected, it would mean that the particle has a small distortion in its internal structure, revealing that charge, parity, and time symmetries have been violated. The reason why this search is so important is directly linked to the conditions proposed by Andrei Sakharov. Symmetry violation is one of the fundamental requirements for generating the predominance of matter. To this day, the violations observed in the decays of beauty mesons and strange mesons are real, but far too small to explain the magnitude of the cosmic imbalance. That is why the detection of an electric dipole moment in elementary particles would be evidence that new sources of symmetry violation exist, beyond those predicted by the standard model. In other words, it would be proof that there is new, as yet undiscovered physics operating in the universe. The experiments that seek to measure electric dipole moments are extreme examples of scientific precision. In the case of the electron, for example, physicists can trap it in specially chosen molecules and observe its behavior in intense electric fields. Any deviation in its alignment would indicate the presence of a dipole moment. For the neutron, ultra-cold beams are confined in containers with controlled electric and magnetic fields. Researchers then measure whether there is any preferred alignment in the orientation of the neutron relative to the applied field. So far, all results have shown values compatible with zero, but the limits achieved are increasingly smaller, narrowing the space for alternative theories. The fascinating aspect of this search is that an electric dipole moment, if found, does not need to be large to have cosmic consequences. Even a tiny difference could, in the primordial universe, have been amplified enough to determine the excess of matter we see today. That is why these experiments, which seem almost impossible due to their delicacy, are among the most relevant in contemporary physics. They represent a direct bridge between laboratory measurements and the philosophical and scientific question of why we exist. The absence of results so far should not be seen as a failure, but as a guide. Each experimental limit narrows the possibilities of theoretical models, eliminating hypotheses and refining the path to future discoveries. The search for electric dipole moments continues around the world, and many scientists believe that detection may be near. If this occurs, it will not only be a technical breakthrough, but also a profound revelation, proof that small imperfections in nature's symmetries determined the fate of the entire cosmos. To deeply understand why matter prevailed over antimatter, humanity has built some of the most complex machines ever created: particle accelerators and colliders. These facilities are true cosmic laboratories, where we recreate, on a microscopic scale, the conditions that existed in the first instance of the universe. By colliding protons, electrons, or heavy ions at speeds close to the speed of light, we can generate temperatures and energies comparable to those that existed fractions of a second after the cosmos was born. In these collisions, particles and antiparticles emerge, which can be studied with extreme precision to search for signs of the symmetry violations necessary to explain cosmic asymmetry. Among the most notable examples are the Large Hadron Collider in Europe and the so-called B factories, such as Super Keck B in Japan. While the Large Hadron Collider investigates a wide variety of fundamental processes, B factories are designed specifically to produce immense quantities of beauty mesons, allowing precise measurement of charge, parity, and time violations in their decays. These experiments have already confirmed that nature treats particles and antiparticles slightly differently, but they have also shown that the degree of violation detected is still insufficient to explain the enormous cosmic imbalance. This realization, far from being an obstacle, is actually a stimulus to search for new mechanisms. The usefulness of colliders goes beyond the production of mesons. They also make it possible to study extremely rare processes that only occur at very high energies, such as the creation of antiatoms and the behavior of heavy particles. Furthermore, they open the door to the discovery of new particles that may be related to a symmetry, such as heavy neutrinos or exotic bosons. Each recorded collision is analyzed by gigantic detectors that function like ultra-high-resolution cameras, capable of tracking the trajectory of every fragment generated in the impact. The richness of these data is such that it often takes years for them to be processed and clearly interpreted. Another central point is that colliders allow us to directly test the robustness of the standard model. If discrepancies are found between experimental results and theoretical predictions during collisions, it will indicate the presence of phenomena beyond the accepted model. These deviations may be small, but it is precisely the subtle details that carry the potential to explain the asymmetry between matter and antimatter. That is why investments in these facilities are considered strategic, not only for particle physics, but also for cosmological understanding as a whole. In summary, colliders and factories dedicated to asymmetry are instruments that combine advanced technology, international collaboration, and profound scientific goals. They represent humanity's attempt to redo, even on an infinitely smaller scale, what happened in the first moments of the universe. With each particle detected, each decay analyzed, we take a step closer to unraveling the mystery of why we exist in a cosmos made of matter. What began as a theoretical paradox has become an unprecedented experimental quest, and colliders are the beating heart of this investigation. Among the most intriguing hypotheses to explain both the absence of intense charge and parity violation in the strong sector and cosmic asymmetry itself is the proposal of the existence of a particle not yet detected, the axion. This hypothetical particle emerged as an elegant solution to a paradox of quantum chromodynamics, the theory that describes the strong nuclear force. This theory predicts the possibility of significant charge and parity violation in the strong sector. But as we have seen, measurements show that such violation is practically non-existent. This discrepancy became known as the strong charge parity violation problem. To solve it, physicists suggested the existence of a new field, called the Peccei-Quinn field, which would naturally give rise to the axion. This field would act as a self-adjusting mechanism, neutralizing the expected violation and explaining why it does not appear in experiments. What makes the axion even more fascinating is that, in addition to solving this specific problem, it may also be directly related to another of the greatest enigmas of cosmology, the nature of dark matter. It is estimated that dark matter represents about 85% of the total matter in the universe, yet to this day, we do not know what it is made of. Axions, if they exist, could fill this role, acting as light particles, practically invisible and abundantly produced in the primordial universe. Thus, in a single hypothesis, it would be possible to simultaneously solve two profound mysteries: the absence of charge parity violation in the strong sector and the identity of dark matter. From an experimental perspective, the search for axions is a monumental challenge. They would interact so weakly with ordinary matter that they would be nearly undetectable. To try to capture them, scientists develop extremely sensitive experiments involving intense magnetic fields and microwave detectors capable of recording tiny signals. The idea is that, under specific conditions, axions could convert into photons, allowing their indirect detection. So far, no definitive signal has been found, but the absence of results is also valuable, as it allows researchers to rule out ranges of possible masses and properties for axions, refining the search. The axion hypothesis also connects to the question of the asymmetry between matter and antimatter. Some models suggest that in the primordial universe, axion fields may have influenced symmetry-breaking processes, providing the additional conditions necessary to generate the excess of matter. In this way, axions would not only be a response to the strong sector problem, or to dark matter, but also an important link in the larger puzzle of our very existence. If confirmed, axions would become a milestone comparable to the discovery of the Higgs boson, redefining our understanding of fundamental forces and the composition of the cosmos. If they continue to elude detection, science will need to find alternative explanations for two of the most persistent problems in physics. Either way, the search for axions symbolizes the essence of scientific investigation, pursuing bold hypotheses that, if true, can radically transform our view of the universe. One of the greatest enigmas of contemporary cosmology is the nature of dark matter, this invisible substance that emits neither light nor radiation, but whose presence is felt through the gravity it exerts on galaxies and cosmic clusters. It is estimated that about 85% of all the matter in the universe is composed of this unknown form, while ordinary matter, made of protons, neutrons, and electrons, corresponds to only a fraction. The link between dark matter and baryonic asymmetry arises from a bold idea. Perhaps the two issues are not independent problems, but different aspects of the same primordial phenomenon. In other words, the processes that favored matter over antimatter could also be directly related to the creation of dark matter. Theoretical models, known as asymmetric dark matter, propose that, just as ordinary matter emerged from a small imbalance between protons and antiprotons, dark matter may also have resulted from a similar asymmetry in an invisible sector of particles. In this view, there would have been dark matter particles and their corresponding antiparticles, which in the early universe almost completely annihilated one another. But, in parallel with what happened with baryonic matter, a small excess of dark matter particles would have survived, forming the current stock that dominates the cosmos. This hypothesis is attractive because it connects two deep mysteries into a single explanation, suggesting that the imbalance between matter and antimatter did not occur only in the visible world, but also in a hidden sector of the universe. This line of reasoning has important observational implications. If dark matter is the result of an asymmetry, its particles would not need to annihilate in detectable pairs today, unlike many traditional models that predict annihilation signals in gamma rays or neutrinos. This may explain why, despite decades of intensive searches, we have not detected direct evidence of dark matter in telescopes or underground experiments. The absence of signals may be, paradoxically, an indication that dark matter behaves in a way similar to baryonic matter, being the result of a primordial excess that simply persists to this day. Another consequence of this hypothesis is the possibility that the density of dark matter is linked to the density of baryonic matter. We observe that the amount of dark matter in the universe is about 5 times greater than that of ordinary matter. This proportion may not be a coincidence, but a direct reflection of processes that occurred simultaneously in the early cosmos. The same physics that tipped the balance in favor of ordinary matter may also have defined the stock of dark matter, maintaining a relationship between the two sectors. There is still no conclusive experimental proof of this link, but many experiments are searching for clues. Underground detectors, particle accelerators, and astrophysical observations continue to look for signs of interaction between dark matter and ordinary matter. If any dark matter particle is finally detected, it will be possible to verify whether its properties fit asymmetric models. Should this occur, we will not only be solving the mystery of dark matter, but also taking a crucial step toward understanding baryonic asymmetry itself. This connection shows that the great enigmas of cosmology may be deeply intertwined. The excess of matter over antimatter and the existence of dark matter may, in the end, be different manifestations of the same primordial imbalance. If this hypothesis is confirmed, we will understand that the structure of the visible and invisible universe was shaped by the same fundamental process. This would reveal that the battle between symmetry and asymmetry, fought in the first instance of the cosmos, determined not only the existence of the galaxies we can observe, but also the silent and dominant presence of dark matter that supports the entire skeleton of the universe. To understand more deeply the origin of the asymmetry between matter and antimatter, we need to consider how the young universe went through successive phase transitions. Just as water can exist in the liquid, solid or gaseous state depending on temperature and pressure, the fundamental fields that govern particles can also assume different states according to the conditions of the cosmos. In the primordial universe, when the temperature was unimaginably high, forces and fields acted in a unified way. As the cosmos expanded and cooled, these symmetries were broken, triggering phase transitions that radically changed the behavior of matter and energy. These transitions were not smooth processes. On the contrary, they may have occurred abruptly, like boiling water forming bubbles that explode inside the liquid. In the case of the universe, such transitions would have created regions with different field configurations, true cosmic bubbles that grew and collided with each other. This scenario is known as the field landscape, and in it, each region can present distinct values of fundamental parameters. It is precisely in these collisions and imbalances that the conditions required by Andrei Sakharov could have arisen. Symmetry violations, baryon number violation, and out-of-equilibrium states. A remarkable example is the breaking of electroweak symmetry, which separated the electromagnetic force from the weak force. If this transition was first order, that is, if it occurred with the formation of bubbles in a previous state, the walls of these bubbles could have acted as real boundaries where particles and antiparticles interacted asymmetrically. This type of process is capable of favoring the production of more matter particles than antimatter particles, establishing the imbalance that persists to this day. The intensity of this effect depends directly on the properties of the fields involved, such as the Higgs field, and also on possible unknown fields. The phase transitions of the early universe do not only leave marks on the amount of matter, but can also generate detectable signals in the present. Background gravitational waves, for example, may have been produced by the collision of these cosmic bubbles. Detecting such waves with future observatories, such as space interferometers, would be a way to directly access the physics of eras so remote that we will never be able to reproduce them in a laboratory. This would open a unique window to verify whether the asymmetry between matter and antimatter is linked to phase transition events. Field landscapes, therefore, offer a framework in which the cosmos did not evolve uniformly, but rather as a transforming mosaic, with regions reorganizing and interacting chaotically. It is in this scenario that perfect symmetry could have been broken in favor of matter. This vision broadens our understanding and suggests that the origin of asymmetry is not only in individual particles, but also in the collective changes that occurred in the fabric of the expanding universe. Thus, cosmic phase transitions are not just details of the past. They are serious candidates to explain why today we exist in a universe built of matter. Among the most fascinating consequences of the primordial universe's phase transitions are the so-called topological defects. These exotic objects are not ordinary particles, but structures that arise when fundamental fields reorganize unevenly in different regions of space. The idea is similar to what happens in solid materials. When a crystal forms, imperfections can appear in its lattice, which remains stable even after the material solidifies. In the case of the cosmos, when the fundamental fields changed state during phase transitions, persistent imperfections could also have appeared, such as cosmic strings, magnetic monopoles, and domain walls. Cosmic strings are extremely thin and dense lines of energy, stretching across cosmic distances. Although they have never been directly observed, theories suggest they may have emerged during the rapid cooling of the universe. These strings could act as catalysts for asymmetric processes, offering privileged sites for different interactions between particles and antiparticles. In addition, the presence of such structures would have generated detectable signals, such as gravitational waves, which may still be echoing in the background of the cosmos. Searching for such signals is one of the goals of modern observatories, since their detection would confirm not only the existence of strings, but also the role of phase transitions in the origin of asymmetry. Another type of predicted topological defect is magnetic monopoles. Unlike ordinary magnets, which always have two poles, north and south, a monopole would have only a single isolated pole. These entities should have been produced in large quantities during the early universe, but so far none have been detected. This fact led many scientists to think that cosmic inflation may have diluted their abundance, making them extremely rare. Even so, the very prediction of their existence shows how changes in the cosmic fabric could have created exceptional conditions for out-of-equilibrium processes, exactly what is required to favor matter over antimatter. There are also so-called domain walls, surfaces of energy that separate regions of space with different values of fundamental fields. These walls, if they had persisted in large numbers, could have had catastrophic consequences for the evolution of the cosmos, as they would concentrate too much energy and alter the distribution of galaxies. Since we do not observe such effects, it is believed that domain walls either disappeared quickly or never formed on a significant scale. Nevertheless, their theoretical possibility reinforces the idea that the early universe was marked by irregularities and temporary structures that may have helped establish the imbalance between matter and antimatter. The relevance of these topological defects to the issue of cosmic asymmetry lies in the fact that all of them represent out-of-equilibrium states, one of Andrei Sakharov's fundamental requirements. In the regions where strings, monopoles, or walls existed, the physical conditions were different from the rest of the universe, creating environments where symmetry violations could manifest in amplified ways. Thus, even though we have never directly observed these objects, their theoretical presence broadens the set of possible scenarios to explain why the universe chose matter. In the end, cosmic strings, monopoles, and domain walls are reminders that the early universe may have been far more complex and irregular than we imagine. What we now see as an orderly and expanding cosmos may have begun as a tangle of defects and imperfections, which disappeared or were diluted over time, but which left their mark on the balance between matter and antimatter. Investigating these remnants is like trying to reconstruct a broken sculpture from fragments, difficult but essential to understand the complete work. Over more than a century of progress, particle physics has built a highly successful theoretical framework known as the Standard Model. It explains with great precision the behavior of fundamental particles, the interactions among them, and the way these interactions shape the reality we know. However, when it comes to the problem of the asymmetry between matter and antimatter, this set of rules seems clearly insufficient. The Standard Model predicts small symmetry violations, as already observed in the decays of strange mesons and beauty mesons. But the intensity of these violations is dozens of orders of magnitude, smaller than what is necessary to justify the colossal imbalance that favored matter in the primordial universe. In other words, if we depended only on what the Standard Model offers us, the cosmos today should be an empty space filled only with radiation. This insufficiency is not only quantitative, but also qualitative. The Standard Model does not predict significant violations of baryon number, one of the indispensable conditions formulated by Andrei Sakharov. Nor does it provide robust mechanisms to generate out-of-equilibrium states capable of amplifying small differences. Even when we take into account processes such as electroweak symmetry breaking, calculations show that the effect is far too weak to produce the observed result. This indicates that the problem does not lie only in the details of the equations, but in the very structure of the model, which may be incomplete or limited in the face of the complexity of the primordial universe. Furthermore, the Standard Model does not cover other fundamental aspects of cosmic reality. It does not explain the nature of dark matter, does not describe the dark energy that accelerates the expansion of the universe, and does not include gravity in its framework. These blind spots suggest that we are dealing only with part of the puzzle. The issue of asymmetry between matter and antimatter in this context is not just another flaw, but perhaps the most direct symptom that we need a larger theory, capable of unifying known phenomena and revealing hidden dimensions of physics. That is why so many hypotheses beyond the Standard Model have been proposed: particles such as axions, heavy neutrinos, supersymmetry, new forces, and exotic fields. Each of these ideas seeks to provide the missing ingredients to satisfy Sakharov's conditions on a cosmic scale. Although none of them has been confirmed so far, the very search is revealing, as it shows that science is in motion, questioning its foundations and expanding the limits of what is possible. In summary, the current set of rules seems insufficient because it perfectly describes the world we can recreate in laboratories, but fails to explain what happened in the earliest moments of the universe. This limitation reminds us that reality is greater than what our current models can encompass. The mystery of the asymmetry between matter and antimatter is, therefore, a living frontier of science, an invitation to go beyond the barriers of established knowledge and seek a more complete and profound vision of the cosmos. Science advances in cycles of theory and observation, and the problem of the asymmetry between matter and antimatter is now at a turning point. In the coming decades, decisive experiments will be carried out, capable of confirming or discarding hypotheses that have been debated for more than half a century. These crucial tests involve not just one area of physics, but extend from the largest particle accelerators on the planet to the most sensitive underground detectors, passing through space telescopes and gravitational wave observatories. Each of these instruments, in different ways, has the potential to offer clues as to why the universe is made of matter and not of pure radiation. In accelerators, the focus will be on expanding the scope of measurements of charge, parity, and time violations in unstable particles such as beauty mesons and strange mesons. The so-called B-meson factories will continue to record billions of decays, looking for tiny deviations from the predictions of the standard model. If new patterns of violation are found, this will represent proof that there are additional mechanisms that favored matter. In addition, increasingly precise experiments with antihydrogen may detect subtle differences in spectral or gravitational properties, revealing asymmetries that have so far escaped observation. In parallel, underground experiments with ultra-sensitive technologies aim to detect neutrinoless double beta decay, the definitive test to determine whether neutrinos are Majorana particles. Confirmation of this hypothesis would strengthen leptogenesis as an explanation for the asymmetry. Detectors located in deep mines, shielded from external radiation, are already reaching unprecedented levels of sensitivity, and many scientists believe the answer could emerge within this decade. Another promising front is the search for electric dipole moments in particles such as the electron and the neutron. The detection of any value different from zero would be unequivocal proof that there are new sources of symmetry violation. Laboratories in several countries are competing to achieve the required precision, and every improvement in confinement and measurement technology increases the chances of success. In the field of astrophysics, space telescopes and gamma-ray observatories continue to look for signs of dark matter particle annihilation. If these signals are detected, they could confirm the link between cosmic asymmetry and the invisible sector of the universe. Similarly, the advancement of gravitational wave observatories could reveal echoes of phase transitions in the primordial universe, providing direct clues about processes that favored matter over antimatter. These different paths converge on a common point. The next decade may bring definitive answers, or at the very least, rule out large classes of theories. This means we are living in a unique period in which science is prepared to confront some of the deepest questions about the origin of the universe. The issue of asymmetry is not just a technical detail of particle physics, but a key to understanding why there are stars, galaxies, planets, and life. Every experimental advance, every new limit established, brings us closer to an answer that will change our vision of the cosmos and perhaps of ourselves. Antimatter, being one of the most fascinating ideas ever discovered by science, often evokes both wonder and fear. Part of this fear comes from the fact that when particles and antiparticles meet, annihilation occurs, releasing 100% of their mass in the form of energy. This process is often described as explosive, and indeed it could release enormous amounts of energy if antimatter existed in abundance. However, this phenomenon is frequently misinterpreted outside the scientific context. Films, series, and science fiction books portray antimatter as an apocalyptic weapon or an inexhaustible energy source, but these representations distort reality. Communicating to the public what we actually know about antimatter is essential to avoid myths and alarmism. The first point to clarify is that the production of antimatter in laboratories is extremely limited. Even in the largest accelerators in the world, such as CERN, The total amount of antimatter created in decades of experiments is less than a grain of dust. This means it is impossible to store sufficient quantities for any destructive application. Moreover, the energy required to produce each antiproton or positron is immensely greater than the energy that would be recovered in its annihilation. Therefore, the idea of using antimatter as fuel or as a weapon is far beyond practical reality. What we handle today in laboratories poses no risk to humanity, as we only deal with microscopic numbers of particles sufficient solely for scientific measurements. Another common myth is to imagine that antimatter is something strange or alien. In reality, it is a natural consequence of the laws of physics. Its existence was predicted theoretically and confirmed experimentally on several occasions. Positrons, for example, are naturally produced in certain types of radioactive decay, and even in processes that occur in the human body, such as in positron emission medical imaging. These uses show that antimatter is not only real, but also beneficial, with concrete applications in medicine and scientific research. The risk, therefore, does not lie in its existence, but in how it is interpreted outside the scientific context. It is equally important to counter the idea that antimatter is a magical solution to humanity's energy problems. Although annihilation theoretically releases a huge amount of energy, the production and storage of antimatter require much more energy than any possible return. There is no technology, not even theoretical, capable of changing this picture in the near future. For this reason, science treats antimatter as an object of fundamental study, not as an energy resource. By communicating these points clearly, we can transform a subject often surrounded by fear or exaggeration into an opportunity for learning. Antimatter ceases to be seen as a threat or fantasy and becomes understood as a tool to explore the deepest laws of the universe. The real risk does not lie in its production, but in the gap between scientific knowledge and public perception. That is why disseminating results in an accessible way, without feeding myths, is an essential part of science's mission. Although it is surrounded by mystery and often associated with exaggerated ideas from science fiction, antimatter already has practical applications in the real world, especially in the field of medicine. The most well-known technology is positron emission tomography, used for detailed diagnoses in the human body. In this examination, small amounts of radioactive substances that emit positrons are introduced into the organism. When these positrons encounter electrons, annihilation occurs, releasing gamma-ray photons that are detected by sensitive devices. The analysis of the distribution of this radiation makes it possible to construct precise images of tissues and organs, revealing metabolic alterations that may indicate tumors or other diseases. This method revolutionized medical diagnosis because it provides information that goes beyond anatomy, showing how the body functions at the cellular level. Beyond medicine, antimatter is also explored in cutting-edge technological research. In physics laboratories, antiprotons and positrons are used to study the properties of matter on fundamental scales. Experiments with antihydrogen, for example, allow direct comparisons of the properties of matter and antimatter, testing fundamental symmetries of nature. These studies do not have immediate practical application, but they are essential for expanding knowledge about the laws that govern the universe and for investigating the origin of cosmic asymmetry. There are also theoretical proposals that antimatter could be used in space propulsion systems in the distant future. The idea is based on the fact that the annihilation of particles and antiparticles releases 100% of the involved mass into energy, making it, in principle, the most efficient way to release energy known. However, this vision faces two enormous problems: the tiny production of antimatter in laboratories and the impossibility of storing it in significant quantities without it coming into contact with ordinary matter. For this reason, these applications still remain only within the field of scientific speculation. Another possible future application is the development of ultra-precise measuring instruments. Since antiatoms make it possible to compare fundamental properties with their matter equivalents, they may help create even more accurate standards of physical measurements, which are the basis of all modern technology. Although we are still far from that point, advances in magnetic traps and antimatter cooling techniques show that science is already taking concrete steps in that direction. In summary, antimatter is already a reality applied for the benefit of humanity, mainly in medicine, and continues to be an irreplaceable tool for scientific research. Its current uses show that, far from being a threat, it is an ally in the fight against diseases and in the pursuit of knowledge. Future applications may seem distant, but each experimental advance brings science closer to fully exploring the potential of this hidden face of reality. The problem of asymmetry between matter and antimatter has made it clear that the Standard Model, despite being one of the greatest achievements of modern science, is not sufficient to explain everything. This realization opened the door for the formulation of alternative scenarios and theories that go beyond the currently accepted framework. These models attempt to provide the missing ingredients needed to satisfy Andrei Sakharov's conditions and explain why matter prevailed in the universe. Many of them are bold, involving new particles, new forces, and even additional dimensions of space. Although there is still no conclusive experimental evidence, these hypotheses broaden the horizon of physics and offer concrete avenues of investigation for the future. One of the most studied proposals is supersymmetry. This theory suggests that every known particle would have a heavier supersymmetric partner. These new particles could expand the possibilities of symmetry violation and offer additional mechanisms to generate the excess of matter. Furthermore, some of them would be natural candidates to make up dark matter, connecting two cosmic enigmas in a single explanation. So far, no sign of supersymmetric particles has been found in experiments such as those at the Large Hadron Collider, but the search continues, and increasingly stringent limits are being established. Another line of investigation involves heavy neutrinos, which may have existed only in the earliest moments of the cosmos. These unstable neutrinos, predicted in extensions of the Standard Model, could decay asymmetrically, favoring leptons over antileptons and giving rise to the process of leptogenesis. Confirming the existence of heavy neutrinos would open an important path to understanding not only the origin of asymmetry, but also the mass of present-day neutrinos, which we already know to be different from zero. Some, even bolder models, propose the existence of extra dimensions. In this framework, the particles and forces we know would be only manifestations of a broader space, invisible to our senses. Interactions occurring in these hidden dimensions could directly influence the balance between matter and antimatter, creating the asymmetry we observe. Although this idea may seem abstract, there are already experiments attempting to identify signs of additional dimensions, such as subtle deviations in the behavior of gravity at microscopic scales. There are also theories that explore new scalar fields beyond the Higgs field. These fields could have played decisive roles in the phase transitions of the primordial universe, providing the out-of-equilibrium states necessary for asymmetry. Some models combine these fields with hypothetical particles such as axions, which already appear as solutions to the problem of charge and parity violation in the strong sector and as candidates for dark matter. These alternative scenarios are part of science's collective effort to expand the boundaries of knowledge. Even if many of them are never confirmed, their formulation is already valuable, as it forces us to confront the blind spots of current theories and to design new experiments. Physics thrives on bold hypotheses tested against reality, and cosmic asymmetry is the kind of problem that demands creativity and intellectual courage. In summary, the scenarios beyond the Standard Model are proof that science is not content with incomplete answers. The fact that we exist in a universe of matter requires explanations we do not yet have, and it is precisely this gap that drives the development of new theories. Each proposal, whether supersymmetry, heavy neutrinos, extra dimensions, or new fundamental fields, represents a possible path towards solving the mystery. And even if many of these paths turn out to be dead ends, some may lead to discoveries that will forever transform our understanding of reality. One of the most promising paths to investigate the origin of the asymmetry between matter and antimatter lies not only in particles, but also in the waves that travel through the very fabric of space-time. The background gravitational waves, remnants of the universe's earliest moments, are a unique window into phenomena that we could never recreate in a laboratory. Just as the cosmic microwave background gives us a luminous snapshot of the cosmos when it was hundreds of thousands of years old, gravitational waves may carry even older information, coming from fractions of a second after the beginning of cosmic expansion. They would be, in essence, the echo of the violent transitions that marked the primordial universe and that may have given rise to the imbalance between matter and antimatter. These connections become clear when we recall that one of Andrei Sakharov's conditions is the need for states out of thermodynamic equilibrium. During the phase transitions that occurred in the young universe, such as the breaking of electroweak symmetry, bubbles of new field states could have formed, collided, and merged. These chaotic processes not only created environments favorable to symmetry violations, but also would have generated intense gravitational waves, capable of crossing space-time without dissipating. If we can detect these background waves today, we will literally be listening to the whispers of the mechanisms that favored matter. Another important connection comes from the topological defects that may have formed during cosmic transitions, such as cosmic strings or domain walls. The movement and disappearance of these exotic structures would also generate background gravitational waves. This means that characteristic signals in the frequency and intensity of these waves may indicate whether the universe truly went through events capable of creating the observed asymmetry. In other words, the study of gravitational waves is not merely a curiosity, but a direct tool to test hypotheses about why we live in a universe dominated by matter. Currently, observatories such as LIGO and Virgo have already detected gravitational waves from the mergers of black holes and neutron stars. These events confirmed Albert Einstein's prediction in the theory of general relativity, but they represent only the tip of the iceberg. The real challenge now is to detect the stochastic background of gravitational waves, that is, the diffuse set of signals coming from multiple cosmic processes in the early universe. Future projects, such as the space-based LISA observatory and networks of next-generation terrestrial detectors, aim to achieve the sensitivity required to record these ancestral waves. If they succeed, they may provide direct evidence of primordial phase transitions and fundamental symmetry violations. The connections between background gravitational waves and cosmic asymmetry reveal that the answer may lie not only in invisible particles, but also in the deep vibrations of the universe itself. Detecting these waves would be like opening a time capsule, revealing processes that occurred at energy scales far beyond what we can access with accelerators. They would allow us to confirm or refute hypotheses about baryogenesis, leptogenesis, and even the influence of exotic fields. More than that, they would remind us that the cosmos keeps its memory not only in light, but also in the silent oscillations of its very space-time. If the problem of the asymmetry between matter and antimatter was born in the very first instance of the universe, then the clues to solving it are not found only in underground laboratories or particle colliders, but also in the sky itself. The cosmos is, in essence, a gigantic natural laboratory. Every photon, every particle, and every gravitational wave we receive carries information about how the universe evolved and about which processes favored matter. For this reason, one of the most important tasks of modern cosmology is to learn to count and precisely measure the signals that the sky offers us. Among the most valuable records are the observations of the cosmic microwave background, which have already proven essential for measuring baryonic matter density and confirming that the excess of matter was established before recombination. The intricate pattern of anisotropies in this radiation is like the fingerprint of the young universe. Each tiny variation in temperature reveals details about the number of particles present and about how matter was distributed relative to radiation. Measuring these fluctuations with greater precision may indicate whether there are traces of symmetry violations beyond those predicted by the standard model, signals that could be interpreted as remnants of the primordial imbalance. Another fundamental measurement lies in counting the light elements formed during primordial nucleosynthesis. The relative abundances of deuterium, helium, and lithium function as a direct test of the conditions of the universe in its first minutes. Observing these elements in ancient stars and in primordial gas clouds makes it possible to verify whether the theoretical calculations match reality. Any discrepancy may indicate the influence of hidden processes that favored matter. This is why telescopes specialized in spectroscopy dedicate so many hours to observing distant objects, searching in the light patterns for the chemical marks left by nucleosynthesis. The sky also provides us with messenger particles. Cosmic rays carry positrons and antiprotons that may originate from common astrophysical sources, such as supernovae and pulsars, but may also conceal hints of deeper processes, such as dark matter annihilation. Detecting a single anti-helium nucleus, for example, would be enough to revolutionize our vision, as it would indicate the existence of antimatter reservoirs somewhere in the cosmos. That is why instruments like the alpha magnetic spectrometer, installed on the International Space Station, continue to record every particle that crosses its magnetic chamber. In addition, gamma-ray telescopes search for signs of annihilation between matter and antimatter on macroscopic scales. If galaxies or large clouds of antimatter existed, the boundaries with ordinary matter would be zones of intense gamma radiation. The silence of the sky in this energy band is one of the strongest arguments against the hypothesis of large domains of antimatter. Likewise, the observation of gravitational waves opens a new channel of information. Background waves originating from phase transitions could confirm that the early universe went through chaotic events, capable of generating the observed asymmetry. Counting and measuring in the sky, therefore, means mapping all cosmic messengers, light, particles, and waves. Each of them reveals a distinct aspect of universal history. Together they form a mosaic that, when properly interpreted, can answer the fundamental question of why we live in a cosmos made of matter. The challenge lies in separating tiny signals from immense noise, in finding patterns amid the chaos of deep space. But it is precisely this task that keeps cosmology in motion, to look at the sky not only to admire its beauty, but to decipher the secrets that determined our existence. As we advance in the study of the asymmetry between matter and antimatter, it becomes increasingly clear that the solution does not lie in gigantic differences or in unknown forces that overwhelmingly dominate the cosmos, but rather in small symmetry breakings, subtle and almost invisible, that manifested in the very first instance of the universe. The paradox lies in the fact that for every billion pairs of particles and antiparticles created at the beginning, only one particle of matter survived. This tiny fraction, 1 part in a billion, was enough to build all the stars, planets, and forms of life. This means that we do not need a colossal rupture to explain reality, but small persistent differences which, under the extreme conditions of the primordial cosmos, were amplified until they defined the destiny of the universe. These small breakings are revealed in phenomena such as the violation of charge and parity observed in meson decays, or in the increasingly narrow limits that experiments impose on the existence of electric dipole moments in fundamental particles. Although results so far indicate very low values, it is precisely in this subtlety that the key may lie. Physics shows that the universe does not need absolute inequalities, but only slight and continuous imbalances. If, in some quantum process, a particle had a slightly greater probability of forming than its corresponding antiparticle, this small bias, repeated billions of times under out-of-equilibrium conditions, may have tipped the scale in favor of matter. From a theoretical point of view, this perspective is consistent with how nature usually operates. It is not common for large symmetries to be broken in a brutal way, but rather for small imperfections to accumulate over time, generating consequences of enormous scope. The very existence of life on Earth is the result of small variations in cosmic parameters, such as the strength of the strong nuclear force or the mass of electrons. If these values were different by even a tiny fraction, the universe would have no stable stars or complex chemistry. This shows that reality depends on delicate adjustments, and the asymmetry between matter and antimatter probably follows this same rule. From an experimental point of view, searching for these small breakings is a work of patience and precision. It is not about detecting spectacular signals, but about carefully measuring particle properties, analyzing patterns in cosmic data, and comparing results with theoretical predictions under increasingly rigorous conditions. The challenge is similar to listening to a whisper amid the roar of a crowd, yet it is exactly this whisper that can tell us the story of how the universe leaned toward matter. In summary, the answer probably lies in small breakings, because the universe is built on minimal differences that produce gigantic effects on a large scale. Each tiny violation of symmetry, imperceptible in a single event, becomes decisive when multiplied by the vast number of processes that occurred in the heat of the primordial cosmos. Finding these breakings is not just about solving a technical detail of physics, but about discovering the origin of material reality itself. The secret of our existence is not found in grandiose explosions, but in the almost invisible delicacy of fundamental imperfections that decided the course of the universe. Reaching this point in the investigation, we can clearly organize the paradox that gave rise to our entire exploration. The fundamental laws of physics indicate that matter and antimatter should have been created in equal amounts in the first instance of the universe. In principle, this perfect symmetry would imply that every particle of matter would encounter its antimatter counterpart, and both would annihilate, leaving behind only radiation. However, the observed reality is radically different. We live in a cosmos full of matter with galaxies, stars, planets, and life, while antimatter has practically disappeared on large scales. The central question is, where did antimatter go, and why did matter survive? This is the paradox of cosmic asymmetry. The attempts at a solution necessarily involve the three conditions formulated by Andrei Sakharov: the need for processes that violate baryon number, the violation of charge, parity, and time symmetries, and the occurrence of states out of thermodynamic equilibrium in the primordial universe. These conditions provide the logical framework that guides the search for answers. Within this framework, several hypotheses have emerged. Electroweak baryogenesis tries to explain the asymmetry from the breaking of symmetry between electromagnetic and weak forces. Leptogenesis proposes that the imbalance began in the neutrino sector and was later transferred to baryonic matter. Models involving hypothetical particles, such as axions and supersymmetric partners, expand the possibilities of violations. And cosmological observations, such as those of background radiation and chemical abundances, offer clues that constrain and refine these theories. The path to a solution, therefore, does not lie in a single definitive answer, but in a set of complementary approaches. Each experimental advance, whether in the search for electric dipole moments, in the precise measurement of the behavior of antiatoms, or in the detection of subtle signals in the sky, adds a piece to the puzzle. Perhaps leptogenesis, associated with the discovery of Majorana neutrinos, will provide the main explanation. Perhaps exotic fields or particles beyond the standard model will reveal additional mechanisms. Or perhaps the answer lies in small symmetry breakings, so subtle that they require decades of refined measurements to be identified. The paradox is simple to state, but immense in its consequences. If there were no asymmetry, there would be no matter, and therefore no life. Understanding how this imbalance arose is ultimately understanding the very reason for our presence in the universe. The path to a solution involves uniting theory and observation, particle experiments and cosmology, microscale and macroscale. This is a global scientific challenge requiring advanced technology, international collaboration, and above all, persistence. In summary, the paradox of matter and antimatter is one of the most fundamental questions of science, and the path to a solution is already being pursued on multiple fronts. It is not just about solving a technical detail, but about answering the most essential question of all. Why does something exist instead of nothing? The search for the answer is, at the same time, an investigation into the remote past of the cosmos and a reflection on the meaning of our own existence. The problem of the asymmetry between matter and antimatter is not just a technical challenge in physics, but an issue that directly touches on profound philosophical themes. It forces us to reflect on why the universe exists in the form we know and why we, conscious beings, are able to observe it. If matter and antimatter had annihilated each other completely, only a sea of uniform radiation would remain, with no atoms, no stars, and no life. This means that our very existence is a direct consequence of a subtle symmetry breaking in the first instance of the cosmos. This perspective brings an existential weight. We are not here by mere chance, but because the fundamental laws of nature operated in a slightly imperfect way. From a scientific point of view, this question reveals the limits of our knowledge. The standard model of particle physics, as successful as it is, does not provide complete explanations for the origin of the asymmetry. This shows us that current science, despite its robustness, is only a chapter in a greater story. Seeking the answer to the predominance of matter is, therefore, exploring the frontiers of the unknown in search of a more comprehensive theory that unites particle physics, cosmology, and perhaps quantum gravity. This pursuit challenges our experimental tools and demands unprecedented precision. but also opens the door to discoveries that may radically transform our view of the cosmos. The philosophical implications also touch on the concept of symmetry. For centuries, we believed that nature was governed by perfect, immutable and symmetrical laws. The discovery that the universe depends on subtle breaks in these symmetries shows us that imperfection is, paradoxically, the condition for existence. Without these small breaks, there would be no atoms, molecules, or life. This realization dialogues with ancient philosophical traditions that already suggested that reality is born from the tension between balance and imbalance. Modern science, by investigating cosmic asymmetry, confirms that the universe is not the result of absolute perfection, but of the delicate imperfection that allowed its evolution. In the scientific field, solving this mystery would have immense consequences. Confirming leptogenesis, for example, would mean simultaneously solving the question of neutrino mass and the origin of baryonic asymmetry. Detecting particles such as axions could explain both the absence of violation in the strong sector and the nature of dark matter. Finding evidence of supersymmetry would open a new era of unifying forces. Each of these answers would profoundly change the course of physics, just as the discovery of general relativity or quantum mechanics transformed our understanding in the 20th century. Ultimately, the issue of matter-antimatter asymmetry reminds us that science does not only seek to describe the world, but also to answer the most fundamental questions about being and existence. We are facing a problem that unites numbers, equations, and experiments with philosophical reflections on the origin of reality. Solving this enigma will not only be a technical advance, but also a revelation about why we are here. That is why, beyond calculations and detectors, the problem of matter and antimatter is also a philosophical journey, an invitation to think about the meaning of the universe and of life within it. Throughout this entire journey, we have explored the origins of the universe, the quantum mechanisms, the laboratory experiments, and the cosmic observations in search of the answer to the enigma: why matter exists and not antimatter. The final synthesis of this paradox shows that the known laws of physics gathered in the Standard Model do not provide a sufficient explanation. They predict almost perfect symmetries, while what we observe is a gigantic asymmetry, decisive for the existence of the material universe. The paradox can be summarized as follows. In theory, nothing should have remained except radiation, but in practice, the entire cosmos is built upon a tiny surplus of matter. This small difference is the reason for everything we know. The path to the solution points in several directions. On one side are the ultra-precise experiments that seek minute differences between particles and antiparticles. On the other, the observations of the sky that rigorously measure chemical abundances and the cosmic microwave background. There are also bold hypotheses involving new particles, exotic fields, additional dimensions, or yet undetected violations of the fundamental symmetries. None of these paths has yet provided the complete answer, but together, they are outlining the space where the truth must be hidden. The synthesis is clear. We already know that the explanation is not in what we know, but in what we have not yet discovered. The problem of asymmetry between matter and antimatter is not only a technical challenge, but an issue that redefines the limits of science. Its solution will require new theories, new experiments, and new technologies, some of which may still be unimaginable. From a scientific point of view, the discovery of a definitive explanation would represent a leap comparable to the theory of relativity or quantum mechanics. We could reveal unprecedented particles, hidden forces, or fundamental fields that would completely change the way we understand the cosmos. From a philosophical point of view, understanding why the universe favored matter is to understand why the universe is habitable and why we exist as a conscious part of this reality. The implications go beyond physics. If the universe had chosen perfect symmetry, nothing of what we call material reality would have arisen. This means that the entire cosmic history, from the formation of galaxies to human consciousness, depended on an almost invisible detail, on a tiny breaking of balance. The fact that we are here to reflect upon this detail is, in itself, a testimony to the delicacy of the laws of nature. The future of investigating this problem will not only tell us how matter prevailed, but also illuminate the depth of our connection with the universe. Ending the narrative about matter and antimatter does not mean putting a full stop. but rather opening space for the continuity of investigation. The legacy of this mystery is to remind humanity that we still do not fully understand the rules that shape the cosmos. The partial answers already reveal valuable clues, but the definitive solution remains ahead, awaiting future discoveries. Science is a collective and intergenerational effort, and solving the paradox will require the union of particle physicists, cosmologists, astronomers, and philosophers. Each generation will make its contribution, advancing a little further in the understanding of the primordial imbalance that brought us here. The legacy of this mystery is twofold. Scientifically, it points to the need to broaden our models and explore unknown territories of physics. Philosophically, it shows that existence is not the result of perfect balance, but of creative imperfections. The universe is made of matter because at some point, symmetry was broken. This break, almost invisible, is the reason we are here, able to reflect upon it. The end of this narrative, therefore, is not a definitive conclusion, but an invitation to curiosity and continuous investigation. As long as we do not have the final answer, the mystery of matter and antimatter will continue to guide us as one of the most fundamental and inspiring questions in the history of humanity. Before ending this video, I want to make you a special invitation. If you have come this far, it is because you have true scientific curiosity and interest in the deep mysteries of the universe. That is why I ask you to leave your like, because it helps a lot to spread this content to more people who also seek to learn. If you are not yet subscribed to the channel, take the opportunity now to subscribe and activate the notification bell. That way you will not miss any of our upcoming long documentaries about science, the cosmos, and the great enigmas of existence. And I really want to read your opinion. Comment below where you are watching this video from and what you think about the theory of matter and antimatter. Your participation is essential to enrich this community and continue this journey of knowledge.